What's up, my fellow atoms? I'm Jacob, and I'm going to be doing the chemistry question of the week today. Thank you, Djia and Nathan, for inviting me. I'm super excited to be here. So, after my chemistry lesson and the practical we did just this week on enthalpy change, I was really interested in what Mr. Main brought up to me as Cooling curves. As you know, we did a practical on enthalpy change, like I said, and we used the maximum temperature and the minimum temperature, and that really doesn't work because, as you know, as the reaction progresses for an exothermic reaction, temperature will increase, and as temperature increases, there's going to be cooling to the surroundings as energy tends to dissipate and wants to be not spread out as much as possible. So it's really important that we take that into consideration. So what we can do, we tried to solve this using a polyester cup, and that's a bit optimistic to solve all your problems. So how I thought would be a really interesting way to solve this that Mr. May brought up was using mathematics and graphs. So this is a cooling curve, and what it does is, as you can see, as the reaction goes on and gets to its maximum, starts cooling down, right? That cooling would take place throughout the whole reaction. So what we do is we forecast back to where the reaction was started to then kind of have a rough estimate of the amount of temperature loss due to cooling would have arisen. So we can do the working like this. So effectively what we do is we have our curve here. This is where our reactant is added. So we can plot this time, nice little just dotted line just to see where it is. And then what we do is, once we get a linear straight line back down after our maximum temperature, we can track back all the way to that point to, like I said, estimate. And then that will give us roughly 60 degrees, we've said, for an example. So we would have missed out 10 degrees to cooling, give or take. So it's really important, as you know, the equation Q equals mc delta T, right? So Q is obviously the energy, right? M is the mass, specific heat capacity, and change in temperature. So what this means is, effectively, the change in the specific heat is the amount of energy to increase 1 kilogram for physics, but for us chemists, grams, to increase one gram of a substance by 1 degree. So if we're missing out 10 degrees, we're missing out quite a lot of energy. So it's really important we don't miss that out, as it is a big impact, because we don't live in an ideal chemist world where energy isn't dissipated and reactions aren't instantaneous. It doesn't work like that. So it's really important we use this. So here we go. Let's say we have a sample of, let's say, 5 grams. So we'd have Q is equal to 5 times by, let's say, what is it? It's 4.18 for our specific heat is what we usually use as our assumption, times by the temperature change of 25 degrees to what would have been 50 degrees, which we are estimating is actually 60 degrees. So what we're going to do is 60 minus 25, and that comes out to, that's 35. So when we do all of that, we end up with 731.5. Perfect. Super cool. Then we know that is in joules. So what we have to do is we have to convert that into kilojoules. So that is equal to 0.731 15 kilojoules, which is super cool. And then we get to the important part, which we've done all this work for, which is our delta H. So that is equal to Q over N. So we don't have our moles because we haven't put it into anything, which we probably should have prepared for a bit more, because I apologize about that. But we would put in our value. Let's say we have, I don't know, what's the usual number? Let's say we have 0.001, because that's pretty usual. They love a times 10 to the power of 3. So we'll have 0.7315 over 0.001. Okay, so that will time Yeah. So, what I almost missed out that I've been caught out on is as we're increasing in our temperature, and it's an exothermic reaction, that means we are having an exothermic reaction, meaning that our delta H will actually be negative as we are giving energy to the surroundings. We are giving energy to the surroundings, increasing its temperature. So we'll have a negative value. So we're going to put a little negative there, and that will take us out to, I believe, just the same value but negative up here. So 731.5, and that is in kilojoules per mole. Super cool. I think it's super cool how the cooling curve works, and it's really important for us as chemists to challenge the way we do things and trying to get closer to the truth. Thank you very much for having me.